Hello, Mr. Sorrentino here, and I'm doing another one of these lecture videos for Math 31. And we first start into Chapter 3, which is going to deal mostly with quadratic functions and move into, um, other polynomial functions from here. And quadratic functions is something that is studied quite a bit in Algebra 1 courses at high school level, and studied even more so in Algebra 2 courses. Um, in Algebra 1 courses, though, you're only considering things dealing with real numbers. In Algebra 2 courses, if you've gone that far in a high school level, you get to study complex numbers a little bit because quadratic functions and quadratic equations are the first time that they actually do show up. And so this particular course decides to introduce them because they will show up in solutions as we progress through this chapter in particular. Um, and the complex numbers start with a new number system. I mean, up to this point, we have our real number system, which we start with, our natural numbers, 1, 2, 3, 4, 5, your counting numbers. And then what you have is you have your whole numbers, which are, sometimes they have a fancy W for that, which is just basically your counting numbers plus the number zero. When you start including their negative counterparts, you have what we call the integers, which are usually abbreviated with a fancy Z for whatever reason. And basically, those are, all your numbers, positive, negatives, and zeros that don't have a decimal or fraction part of it. But then, those numbers, as well as many other numbers, can be represented as fractions, and it can have fraction parts to them, and they're called the rational numbers, which oftentimes um, they're given the symbol Q for rational. Um, so basically, any number that can be written as a fraction is a rational number. As a subset, there are numbers that cannot be written as rational numbers. They're called the irrational numbers, sometimes given the symbol Q prime. These are like square roots of non-perfect squares, like the square root of 2, the square root of 3. Numbers that cannot be written as fractions. Another famous one is pi. We'll talk about another one when we get into exponential functions, the number e. Um, but it's these combinations of numbers together that make up what we call the real number system. And basically, real numbers are the types of things that come up in any of the calculations that you would tend to do in any math course you had through much of your high school career, certainly most of all of your grade school careers and elementary schools. Um, and real numbers can often be portrayed as being something that's on a number line or in a coordinate system and things of that nature. Well, now there's another system that we're talking about. We're talking about the number I. It's an imaginary number. Not really a good choice of words because some people think it's a number that's been someone's imagination. That's not really the case. It just means that it's not real. And it's not real because it's the first instance where we're allowed to take the square root of a negative number. In real number system, we can't do that. So, um, you know, when we talk about imaginary numbers, this is now allowable. And calculations allowing that to happen, you start getting into fields of electrical engineering and things like that. These numbers have their uses. Um, I couldn't tell you exactly how much so because I did not study electrical engineering, but I do know that's one area where they have usage. It's also fourth dimensional mathematics, so certain theories in physics and things of that nature also will use complex numbers as part of their calculations as well. It's the combination of the imaginary number system and the real number system that makes up what we call complex numbers. So that's what a complex number is. It's a combination of the real and imaginary number system. So that means that any number we've dealt with up to this point, which of course were real numbers, they're also complex numbers. They just have a zero for their imaginary part. And that's what the format of a complex number looks like. It has what we call the real part, and it has the imaginary part, which the imaginary part is just some real number multiplied to a power of I. So that's what a complex number is. And we're going to start looking at situations when we're doing various math and coming up with solutions that will be complex numbers. But before we get too far into that, we need to think about more about what this imaginary number I is, and that's really the only number that exists in the imaginary number system. The other things are just multiples of that one number. So let's have a look at what I is and powers of I. As I said before, I is, the imaginary number I is kind of unique because it's really the only number in that number system. And we start dealing with powers of I, just like, exponent rules, which, were presented to you in other algebra courses prior to this. Anytime I have a number raised to the first power, like I have here I to the first power, we're going to assume that rule holds true as well for this. So I to the first power is just I. And as part of the definition you've seen above for the number I, obviously if I equals the square root of -1, if I were to square that, which means I would end up squaring this, as a result, I squared, the square root and the square would cancel, leaving me with a -1. So I squared is just -1. So if I square an imaginary number, I end up with a real number, -1. The rest of these is stem from the fact that, okay, well, if I have I cubed, much like, exponent rules before, anything to the third power can be expressed as something to the first power times that same base to the second power. And we know what these are. I to the first power is just I. I squared is -1. Anything times -1 is just a negative version of itself. So this would be known as -I. I to the fourth would be like having I squared, which means that's -1 squared, which equals 1. Once we get to other powers of I beyond this, much like, I to the fifth, I can write this as I times I to the fourth. We know that I to the fourth is just 1. So this again is I. So I to the fifth is the same thing as being equal to I. So there's a pattern to this. Powers of I are only going to result in one of four things. It's either going to be I itself, -1, -I, or +1. Continue with this, I to the sixth power would be like having I to the second power times I to the fourth power, which would be -1 times 1, which equals -1. I to the seventh power would be I to the third times I to the fourth, which would be -I times 1, which is -I. You can see the pattern keeps going in the same way, and that goes forwards and backwards. So when I look down here, I see like the previous the number that was the power of I previous to I to the fifth was 1. Well, much like the same way, since I to the first is also equal to I, its previous number, the power, is going to be 1 as well. And this goes along with the same rule we have for exponents, because any number to the 0 power, now this even works for imaginary numbers, equals 1. So anything to the 0 power equals 1, no matter if it's real or imaginary. Any real number, which means whether it's natural, an integer, a rational number, anything to the 0 power equals 1. It also works in the imaginary numbers. And of course, this would be a -I. So this pattern continues in both directions, knowing that, these are basically the four values that I or powers of I can take on. The reason why we have to be aware of this is we do various math with these. We may end up with powers of I, but remember, a complex number has to have that A plus BI format. There is no power here, okay, other than 1 being assumed. So if I'm given some sort of power of I got to write it as either a number or I got to write it as some multiple of I. So, that this is the format a complex number has to be written in. I can't write a number like, 3 plus I plus like 2I squared. That's not a complex number. you know, a complex, and this is the first time when we deal with complex numbers, we have a number expressed as two separate terms. So there's a lot of things that we're going to be dealing with this that you have to keep in mind. That now two terms make up a single number, and it has to have a specific format. But we're going to get into that as we go through this lesson. So let's see, how we can evaluate even higher powers of I. So here we have a question asking us to evaluate what I to the 244th power is, and to evaluate what I to the 1053rd power is. Obviously you're not supposed to continue this list we had up here until you get to 244, until you get to 1053. What we're going to do is we're going to take this number here, 244, and I'm going to divide it by 4, because there's 4 different numbers that a power of I can take on. If I divide that, I get 6 times 4 is 24. Bring down the 4. 1, which gives me a 0 here. That tells me that I to the 244th power can be written as I to the 4th raised to the 61 power, which means that that's 1 to the 61 power, and if I multiply 1 to itself 61 times, I'm still just going to end up with 1. In a similar fashion, if I take 1053 and divide it by 4, now carry through, I'm just going to do this in fast motion. I get, divided by 4, I get 263 and a remainder of 1, which means that I to the 1053 can be expressed as I to the 4th raised to the 263rd power times I to the 1st, that remainder. That means I have 263 I to the 4ths, that's the division of 4, and then I'm going to have another times I, because remember when I multiply powers of I, or multiply powers of the same base, I add the exponents. When I take a power of a power, I multiply them. So, this would give me 4 times 263 would give me 1052. So I to the 1052 times I to the 1st would give me the 1053. Well, again, this is just 1 in here. 1 raised to any power is 1. I to the 1st, which is just I. An even more shortcut, I'm showing why this works, because you could split it into something in terms of I to the 4th power. In the end, if you want even a bigger shortcut, is once you carry through the division, whatever your remainder ends up being, that's the new power of I that's going to be equal to. So I could just as easily say, okay, from this division, I know this equals I to the 1st, which just equals I. And from here, I could have said, okay, well, that just equals I to the 0, and anything to the 0 is just 1. So that's even a shorter shortcut. I just gave those other things as explanations. So powers of I should not be that difficult. All you do is divide by 4 and pay attention to whatever the remainder is, and there you got it. Now, this section 3.1 also goes into how to perform various operations with complex numbers. And you're going to find out that, some of the things that you do with them are very similar to other instances, especially if you're dealing with like terms and whatnot. So let's have a look at that now. So if you're asked to find the values of the following, and you know that complex numbers are allowed to be used, either by the context of the question, or it does, I mean, sometimes it's just going to say if they want only real numbers, let's say just find the real solutions or the real values. Here they're just saying find the values. So if I had the square root of negative 36, I could look at it as doing that this is equal to, based off of other rules of radicals, I can split this, since this is equal to the square root of negative 1 times 36. I can split a radical through multiplication. So I can have the negative 1 out here. I can have the 36 here. We know that the square root of negative 1 is I. That's the definition of what I is. Of course, the square root of 36 is 6. So we would express this as 6I. For B, I can't, regular. If I just had a regular parenthesis, I could distribute a negative into it. But, this square root symbol is not a regular parenthesis. I just can't combine the two together in some way. So, I have to look at this as negative 1 times the square root of negative 1 times 7, which I can express even further as negative 1 times the square root of negative 1 times the square root of 7, which is negative 1 times, again, the square root of negative 1 is I, times the square root of 7, which we would just end up writing as negative I times the square root of 7. Oftentimes when we write numbers that have an I term, where the real number being multiplied to it, the B value for this instance is an irrational number that has to be written in terms of a square root. Because we could evaluate this square root of 7 and get some decimal and say it's that decimal times, or negative of that decimal times I, but that would be an approximate. Oftentimes you're going to see, as we get into these later chapters in this course, we're looking for exact answers. And exact answers, if they're irrational, I'm not going to be able to write them as a fraction or a simplified fraction or a decimal that I can either express as it terminating somewhere or has a repeating pattern, because it won't, because those are signs of a rational number. So, we'll often leave the square root of 7 alone and say that's the number being multiplied to this. What you'll often also see, though, when I have this radical involved in the answer, we tend to put the I before the number. And that's because, technically, if you want to have it look like this form over here, you would say this. But where some people have issues is you have to make sure that you're clearly showing that this I is not underneath that square root symbol, because i's can be square rooted. We're not going to get into that in this course. We're not going to be square rooting any complex numbers. They can be, but we're not going to do that in this particular course. But keep in mind that since it can be done, if you wrote the answer like this and show that that square root symbol is going over the I, you're going to have a problem, because these are not the same thing. Okay? So, you have to be really careful. Like, if you just extend this too far and you're extending it above the I, you're expressing a totally different answer. Getting to the last example. There's a couple ways to handle this, because, if I could split a square root into two other square roots, and if I have two square roots, I can combine them into one through multiplication. It gets a little tricky when you deal with the i's, though, because you have to be very careful, making sure that you are explaining what happens to the symbols, because sometimes multiplying powers with or roots with negatives in them could cause issues if you don't handle them correctly. I mean, one way to handle this is to say, okay, well, that's going to be equal to the square root of negative 3 times negative 12, which equals the square root of 36, which equals 6. However, that is not the right answer or the right procedure to use. And here's why. And I'm going to explain that using the calculator. So pulling up my calculator and putting it into the LCD so you can see it a little better. So you can see this a little bit better. First of all, if I'm in my, depending on what kind of calculator you have in front of you, if it's a newer version, you might see this menu that you see written up here. Otherwise, you might have to go into your mode area to figure out what's going on with this. But you can see I'm set up to be in my real, to produce real numbers here. And so first of all, if I try to just do the square root of -3, if I try to hit enter in this region here, I'm getting non-real answers, and that stands to reason because, the square root of -3 is not going to be a real number. The square root of -12 is not going to be a real number. So in real mode, as it says here, I mean, you may not get as much of an explanation here. In real mode, all calculations must result in a real number. So that means it's kind of telling me that, well, if I want to carry through this calculation, I have to put it into another mode. So I'm going to go to here. And before I hit enter this time, I'm going to go to mode. And if you look down at this level right here, it says real. You have this over here, which is another mode that you get kind of into when you deal with pre-calculus. But the one in the middle says A plus BI, which we kind of know now from our experience. That means it's a complex number mode. So if I go there, it's going to say A plus BI. So now I'm in complex number mode. And if I carry through this calculation, it says -6. Remember, we got +6 when we did that calculation because we did not handle it correctly. The reason why we didn't handle it correctly is once I take into consideration that I can carry through the multiplication, because I'm assuming these are complex numbers, I have to treat them as complex numbers, which means I have to first make them into complex numbers, or in this case, non-real numbers. So when you're dealing with square roots of negatives, your first goal is to really put them in terms of I. That's the very first thing. So anytime you see a square root of a negative number involved, you have to put it in terms of I first before you do any multiplication. And that makes sense because putting it in terms of I means you're taking care of the square root first. Okay? And according to the order of operations, exponents, which square roots fall into that. Square roots are technically raising something to a 1/2 power. We'll get more into the exponential rules as we move through that, but keep in mind that a square root is raising something to a 1/2 power. I had to take care of the square root first and then do the multiplication according to my order of operations. So if I follow that logic and handle this correctly now, just do a purple. There we go. I know that the square root of -3 through other things I've did on this one and this one, I'm not going to write as many steps. The square root of -3 is going to be I times the square root of 3. As a shortcut to get rid of a negative underneath the square root, just write an I on the outside, and that makes what underneath the square root a positive. I'm just doing it in less steps instead of writing, writing this step and then writing this step and then getting that I eventually anyway. Really can't do anything with the square root of 3 because, well, it's not a perfect square, and if I took the square root, I'd get some kind of sort of decimal. Times, and I do the same thing with the square root of -12. I put an I on the outside, and I just put a +12 in there. With a little bit of rearranging, because multiplication is commutative, I'm going to have I times square root of 3 times square root of 12. I times I is I squared. The square root of 3 times the square root of 12 being regular square roots, I can multiply those together now because that's a characteristic that works in real number system. It's been established in a real number system. We've already established it doesn't work in a complex number system. I squared is -1. 3 times 12 is 36, And the square root of 36 is 6. I'm going to have negative 1 times 6, which gives us the negative 6 that the calculator had pointed out was, in fact, the right answer. So when you're dealing with numbers you know are going to be complex numbers, you see those negatives underneath the square root, you have to put the numbers in terms of I first and then carry through the computation. So that's a standard you have to kind of get used to, so you don't end up with getting a number that's the wrong sign or getting just a wrong answer in general. So now let's look at doing operations, other operations with these imaginary and complex numbers. So we're going to look first at addition, subtraction, and multiplication, and we'll talk a little bit more about division when we get to the last part of the examples for example 3. Here in part A, I see 4 minus the square root of negative 49 plus 3 plus the square root of negative 4. Now, assuming I'm allowing the square root of negatives to occur, that means I am considering this to be a complex number solution. So once I make that realization, I'm going to turn these square root of negatives into, simplify them and put them in terms of I. So for the time being, I'm going to have 4 minus, move the I to the outside, square root 49, plus 3 plus I, square root 4. And of course, the square root of 49 is 7, so this is going to be 4 minus 7i plus 3 plus square root of 4 is 2, so 2i. So I'm adding these two complex numbers together. Now remember, as I do this, the answer has to have a format that looks like a plus bi. Not saying there has to be a plus sign here. If this number here ends up being negative, then I'm obviously going to have a minus between them. Or if I get with the first number being negative, it means I might have a negative in front of the leading number. But I have to have clearly a real part and an imaginary part. And the only exception I'm going to have if one of those is missing, that's because that particular value becomes 0. So as I get into finishing this, this is like having, again, since these are two-term numbers, and since I'm doing an addition here, I don't have to worry about the parentheses as much at this point. This is like having like terms again. Early in algebra, you have to make sure you combine like terms. Same thing here, and that's the one rule you have to remember when you do addition and subtraction, and even some part of multiplication as well, is that you have to remember that you're going to combine like terms. And so that means that, like terms in this case would be your real parts. The real numbers are like terms because they're real numbers. So like the 4 plus 3 becomes a 7. The imaginary parts are their own like terms. So a negative 7i plus a 2i is going to give me a negative 5i. So it's like adding a negative 5i, which I'd write even more simplified as 7 minus 5i. So that's the solution. Complex numbers, under most circumstances, are going to be two terms. They're going to have a real part and an imaginary part. So your answer should be written with two terms. This is just one number. It's a concept that sometimes students have trouble with complex numbers because they're numbers that are written in two terms. Subtraction works the same way, really. The only thing is, I can clear these parentheses on the first one because really nothing's happening to that first grouping. This negative, this minus here, means there's a minus 1 being multiplied to this, so this has to be distributed. So I do have to have a minus 9, and I have to have a plus 4i here. And then it's just combining like terms again. 6 minus 9 is a negative 3. 11i plus 4i is 15i. So your additions and subtractions are very similar to just doing, combining of like terms and making sure you distribute appropriately. And I can confirm this on my calculator as well. I can be in real mode or imaginary mode, doesn't matter. I'm going to put mine back in real mode because most of the time, most of the calculations that one tends to do is in real mode. So I'm just going to go to mode and put it back down here to real. Because I can enter in imaginary numbers in real mode. That just says temporarily treat this as a complex number. So if I take like the first one, once I did my simplification, oh, let's do the second one. If I want to do 6 plus 11i, now I is a term that's found right above the decimal point. You'll see it's written up here in blue. So if I hit second in the decimal point, I'm going to get an I to show up there. And then I subtract the 9 minus 4i. Once I start putting those i's in there, this is going to tell the calculator, even though I'm in real mode, to write this as a complex number. And as you can see, I get the exact same answer as we have right here. So addition and subtraction is just basically combining like terms. For multiplication, let's move this over. For multiplication, the only real difference is, I mean, there's going to be some combining of like terms as well. The only thing I have to make sure I'm doing a lot of when I multiply complex numbers is that I'm distributing correctly. So for instance, if I do 4i times 12 minus i, this is a complex number. It's like having 0 plus 4i. Of course, the real part would be 0. 12 minus I would be like, it's like saying 12 minus 1i. So if I carry this through, I'm going to need to distribute this 4i. Both terms have to be multiplied by 4i. If I had two terms like in D, I'm going to have to do basically distribute the 10 and then distribute the minus 3i in the same process we know as FOILing. So here I'm going to have 4i times 12, that's 48i. 4i times negative I is a negative 4i squared. Again though, I have to have these written in the format a plus bi. There is no I squared in a complex number format. But this also goes back to what we just learned about. I squared is the same thing as negative 1. Which means I have 48i. Negative 4 times negative 1 is a positive 4, so this becomes a plus 4. And of course, I want to write it in the exact format. I'm going to have 4 plus 48i. So that's the number. That's the correct answer written in the correct format. And again, you can kind of use a similar process I just showed you before to do that on your calculator to check it. So these can all be checked on the calculator as well. And by all means, do so you get used to, making sure you're handling it correctly. This one here, 10 minus 3i times 8 plus 5i. I'm going to distribute again. So the 10 gets distributed. So I'm going to have 10 times 8, which is 80, plus 50i. And then this gets distributed to both. So negative 3i times 8 is a minus 24i. And negative 3i times 5i is a minus 15i squared. These are like terms. So I can say that 50i minus 24i is going to give me 26i. But again, this I squared is not part of the structure of a complex number. I have to get this eventually in a plus bi format. Again though, I squared is the same thing as negative 1. So this is the same thing as having 80 plus 26i plus 15. And now these are like terms because they're both just real numbers. So I'm going to have 95 plus 26i. Remember, if it's attached to the I, it's not a like term with anything that's not attached to the I. I can only combine things that have i's attached to them or things that don't have i's attached to them. I don't count the I squares because that should be simplified anyway. So this is the final answer. And you are expected to simplify it down to this format. Otherwise, you're not expressing a number as a complex number. So we've got a couple other multiplications as we go along with this example. 5 minus 2i squared. A lot of students will do wrong because they handle the squaring wrong. And it kind of gets back to some of the issues they had when they dealt with quadratics, in general. There's two terms here, a bit the wrong way of handling it. I'm just going to do this in kind of a yellowish looking color. Some students would say, well, that's going to be 5 squared minus 2i squared. They do something cockamamie like that. That's going to be 25 minus, they get the 4. They might remember to do the I squared as well. Sometimes they don't square both parts of it. That's not the right answer because that's not in the right format. And they'll say, okay, 25 minus 4 times negative 1, which equals 25 plus 4, which equals 29. Now you're going to see part of that is used, but the thing is, you're not squaring it correctly because squaring is not distributive. Only multiplication is. So to handle this correctly, because again, this is wrong. To handle this correctly, I'm going to have to think of this as being 5 minus 2i times 5 minus 2i. Now I showed it in different steps before over there, but as a distributive, but I'm essentially foiling this. So, as I go through and do this, 5 times 5 is 25. 5 minus 2i is a minus 10i. Negative 2i times 5 is another minus 10i. And negative 2i times negative 2i is going to be a positive 4i squared, which, since I squared becomes a negative 1, becomes a minus 4, because that's 4 times negative 1. And now I combine like terms. The 25 and the minus 4 go together. Negative 10i minus 10i would be a negative 20i. And that's the answer. So you see some of the numbers came up that I had over here, but they combined differently. The symbols got changed. Some people would change the minus to a plus over there, maybe get the 21 part of this, but they would also they would miss the non-real part of it. And most of the time when you do multiply complex numbers together, you're going to get a complex number with both a real and imaginary part. There's one exception to that, and that's what F is dealing with. In F, let's go to an even different color yet. Let's go to a lighter blue. These, you notice that they both have the same real part. They both have the same digit in the imaginary part. Really, the only difference is that one has a plus between them, the other one has a minus. These are called complex conjugates. Complexes are complex numbers. Conjugates are basically anything that has two terms, where the only difference between the two is that the symbol between your two terms is an opposite sign. These are complex conjugates. Let's see what complex conjugates have a very special relationship when I multiply them together. So let's see what that relationship is. So I'm going to do the foiling like I did before. 4 times 4 is 16. 4 times a minus 3i is going to be a minus 12i. 3i times 4 is going to be a plus 12i. And of course, 3i times a negative 3i is going to be a minus 9i squared. Now, of course, this is still not in our usual a plus bi format. 16, well, a minus 12i and a plus 12i, they would cancel. They become nothing. I'll put a plus 0 there. Or I can say 0i, or just 0. Again, I squared should not be part of the structure, but I squared is negative 1, so negative 9 times negative 1 is a plus 9. Now again, there's really no need to write a 0i there. It just means that I don't have an imaginary part, and 16 plus 9 is 25. Something like very similar to this will happen with all complex conjugates. If I multiply complex conjugates together, what ends up happening is this inner part, the O and the I part of the foiling process, are always going to cancel out. And that O and I part of the foiling process is what creates the non-real part of your complex number. They're always going to cancel, so basically when I multiply complex conjugates together, the result is a real number. I don't have a non-real part anymore. And that's important to remember when we get into division. So let's do the last couple of parts of this example, which deal with division. So far the addition, subtraction, and multiplication didn't behave too much unlike any additions, subtractions, and multiplications I had done in the past. Because since we're dealing with numbers that are essentially more than one, have two terms to them, I just have to make sure I'm combining like terms and that I am distributing correctly when I multiply. Division works considerably different than division of just real numbers. When I divide real numbers, I'm looking to see like how many times one number can go into another. That's really not the way we handle complex numbers. When I have a division of complex numbers, which first of all, they're always going to be represented looking like fractions. So this fraction of 8 minus 3i in the numerator and 2 plus 5i in the denominator is basically the same thing as me saying 8 minus 3i divided by 2 plus 5i. So this is a division problem. I'm not looking to see how many times 2 plus 5i goes into 8 minus 3i. That's a more complicated way of trying to handle it, and it's hard to like kind of manipulate things to make that happen correctly. My goal for a division is the following. I had alter there before, but it's actually simplify. Um, because I want to simplify the fraction, which means I want like when I simplified fractions before, like really easy cases when I had like 3/6 and I would simplify and say that's 1/2. Those are the same value. But 1/2 has everything in lowest terms. That's why they would call it simplified. Well, when I simplify a complex number, which is what I do when I try to do a division, my division's goal is to simplify this number. I don't want a denominator having a complex number. I want the number in the denominator to be real, which means I want 2 plus 5i. I want to do something to that so that it becomes a real number. So I have to think, and this kind of goes back to what we just talked about. If I wanted to make the bottom a real number, I would multiply the bottom by its complex conjugate. So instead of 2 plus 5i, I'd multiply it by a 2 minus 5i. Recognizing over the fact that doing so is going to eventually make the bottom a real number. I just can't multiply a denominator of a fraction when I want to simplify. Because simplifying means I'm changing, I'm altering the fraction, but it's still equal to the same amount. If I just multiply the denominator by something, I'm essentially dividing that number by something. And when I divide a number by something, it's going to change it because this is obviously not equal to 1. So in order for me to, simplify rather than alter the number, I'm also going to multiply the top by the 2 minus 5i as well. And the reason for that is when I do so, I'm now officially multiplying this fraction by 1. When I multiply something by 1, nothing happens. The value remains the same. So I'm going to be able to rewrite this with a real number in the denominator and having something new in the numerator, but it's not going to change the value of what this number is. So going on from there, I'm going to need to FOIL out the top. So I'm going to have 8 times 2, which is 16. 8 times a minus 5i is a minus 40i. A negative 3i times 2 is a minus 6i. A negative 3i times a negative 5i is a plus 15i. 2 plus 5i times 2 minus 5i. Again, I'm going to do the FOILing for that. And then before that, 15i should be 15i squared because negative 3i times negative 5i is negative 15. It's positive 15i squared. So I'm going to have 16. Negative 4, a negative 40i minus 6i is going to be a negative 46i when I combine those like terms. The 15i squared really shouldn't be part of this. 15i squared is the same thing as negative 15. Down here I'm going to have 4. The minus 10i and the plus 10i cancel. We expected that to happen because that's what makes the bottom number real. The imaginary parts go away. And I'm going to have a minus 25i squared is negative 25 because I squared is negative 1. So 16 plus a negative 15 is 1 minus 46i. 4 minus a negative 25 is the same thing as 4 plus 25, which is 29. So I now have the denominator being a real number, not a complex number anymore. I'm not done though, because again, remember, these answers should be written A plus BI format. This is not A plus BI format. This is A plus BI all over some other number. We'll say C. So going back to some rules we used before, if I have two terms being divided by a single number, that division is distributive. So I can rewrite this as 1 over 29 minus 46 over 29i. And that is the correct answer. And to verify, I'm going to bring up my calculator again. Just to show. If I do 8 minus 3i divided by 2 plus 5i. Now I get some nasty decimals here, but I do have a fraction command on my calculator. And you can see it's 1 over 29 minus 46 29ths I. So it comes out to be the same answer, and you could definitely check this on the calculator as well. Now H, I can handle the same way, but H is only here as an example to kind of point out to pay attention to what goes on around you in the problem and take really good looks at it. Because, you know, I can certainly multiply the top and bottom by 5 plus 3i if I want to and carry through this quite simply. But if I pay really close attention and look for this occasionally, it's not going to happen frequently, but look for it. It'll save you some work. I notice that the top is exactly 2 times 5 minus 3i. I can factor out a 2 from 10 minus 6i and end up with 5 minus 3i as a result. And going back to my fraction simplification rules, well, if I had the same thing on top and bottom of a fraction, they cancel. This becomes this cancels, this becomes a 1. So I essentially have 2 over 1, which is just 2. Oh, I don't know what caused that jump there. Pull that back. But just to finalize this, you know, so although it will not happen frequently, it might happen in like maybe one of the homework problems if you look carefully enough that are assigned to you to do and practice. You know, if you look closely enough, you might be able to find this. Now, if you go through and multiply the top and bottom by the conjugate 5 plus 3i, you should get to the same answer. But certainly, sometimes shortcuts can be taken. Just make sure they're legitimate shortcuts. You can see some of the calculator notes written down here at this point. which are kind of summaries of what I've shown along the way. Uh, when I was doing these calculations. So that's basically what you have to know about complex numbers. They have to be written in that A plus BI format. You now know the procedures for adding, subtracting, multiplying, and dividing them. You also know how to figure out various powers of I quickly. And those are the skills about complex numbers that you're expected to come away with. So that's all I have for this video. If you have any further questions dealing with complex numbers or 3-1, please make sure to reach out to me or come to my office hours or ask about them in class. Until I see you in either class or office hours or until the next video, I'll see you around. Have a good day, everybody.